Thank you all for coming. I'm happy to be invited here by Scalable Bay to give this talk. So first off, who am I? I run sales, solutions engineering, training, partnerships, et cetera, at a company named Fermyon. We'll talk more about what Fermyon does slightly at the end, but what I want to talk today about this white paper I wrote. Background: previously, I was an early employee at Puppet and HashiCorp, a company called Prisma. I'm currently doing an executive MBA at UC Berkeley. I don't know if that matters in any possible way, but everyone in my cohort tells every possible person they're doing it, so I guess I might as well too. So I wrote this white paper. I'll put the QR code up at the end too. This came out in September. Really, I was thinking about the cost and performance optimization on LLM inferencing. And let's kind of dive into the why of this paper and go through this. So as I think everybody who's not living under a rock knows, GPUs are really, really expensive. And LLMs tend to take a lot of GPU memory, and they require the most expensive ones. You know, good luck getting a spot instance. Pretty much AWS and Microsoft have said that's just not happening anytime in the near future. So you're paying full freight for those GPUs if you want them. Tools like SkyPilot can help you go find the cheapest GPU today, but you still are going to go out there and go find it somewhere. And then obviously we've all heard of OpenAI's ChatGPT, and there's a bunch of other competitive offerings that charge models on a per token instance. This can often be much cheaper if you're not going to fully utilize your GPU. A lot of what we're going to talk today is about the challenges of fully utilizing your GPU. But ultimately, like, those problems that you would have doing that are the same problems that the vendors you're buying from, like OpenAI, are having those challenges of how do we deal with scale on things that are user impacting. So I'm going to go through that and figure out how that applies to your costs and how you can control that. So really the big thing to think about is, like, what are the variables that I care about the most, right? Do I care about the total time it takes to complete the inference? Do I care about the startup, the cold start time for the inference? Do I care about accuracy? Am I trying to reduce costs? Like, what are all of those pieces that you're trying to control for in your particular use case? Because the architecture choices you're gonna make are gonna have impacts on that. And so if your workload can run at any time, right? Like, and I think it was Microsoft, someone just launched an inferencing service where they're like, hey, we'll do it in the next day for you. If you have an instance where, like, I don't really care when this gets done as long as it gets done in a day, you know, there's competitive offerings for that. And that's really where it's what's your workload, right? And we see a lot of these things like batch job and training that can happen at the cheapest possible times that we don't really care when it happens. We don't care if it happens quickly. We don't care if there's a delay. We can do it all at once, hold it steady state. That's great. And then we have other issues, and there's a lot of the enterprises out there today that are building, pretty much everyone has an AI play today, trying to think about what is the way that we can use large language models and AI inferencing at our company. And a lot of those are trying to build things that are user-facing. So one example of a company I'm working with today is trying to do basically natural language SQL generation, where they have the user, they have a big database with all the information about the user's systems, and they're like, hey, I want people to be able, who are not SQL admins, to ask questions of this database. So they want to do it in natural language, and so they're trying to use AI models to generate SQL from that. But because the user's doing it, right, you can't wait a day for that response to come back. You need to do this in real time. And when you have that real-time implication, your architectural choices start changing, and you have to start making decisions around how do I balance the cost with the speed that I need this to occur in. And so again, OpenAI, token-based things are often one of the cheapest ways to do this, and they give you the ability to scale from I'm not paying anything because I'm not doing any inferences to I can do a bunch of inferences and I'll pay for those, and then I'll come back down. Of course, that comes at the cost of flexibility, right? Well, that didn't work immediately for me. Like, let me go get my own model. So this slide. And I've seen this a bunch where people, they built a thing around OpenAI's API. They gave it a question. It gave them a meh answer, just enough to be useful for an internal demo, but not product worthy. And the first thing that people think of is I need my own model, or I need to go do some custom training. And they kind of go down this very the very heavy route of doing either lower weights or fully fine-tuning a model. And that puts them into the place where I'm like, I need to then host it because I don't have options otherwise, or the options I do have are relatively limited and more expensive. So it was one of the things that I like to push a lot here is like the first thing you do before you go down that route is really think about all the things you can do for prompt engineering. There's a lot that you can achieve with ChatGPT and the other token-based models that are not just, hey, I gave it a prompt, it didn't understand the prompt, I give up now, right? Temperature is a big piece to this, right? Like that really, it varies the likelihood of what word it's gonna pick next, right? We don't always wanna go at a temperature of 0, we're gonna pick the most likely word every time because we end up with very bland responses that are often quite repetitive, right? And we have other variables like top P, top K, we have a penalty for repetition, all of these things we can control. And then we see increasingly, like the way you ask a question really impacts the answer you get out of that. And so doing things that don't really make sense to tell a computer can actually be helpful because of the way it gleaned all of the data. So there's a study that came out saying like asking the AI model to take things step by step often gets more clear results. There's another article I read the other day where absolutely just cursing at the thing actually got even better results. You know, it's kind of weird the things that fall out of this black box of large language modeling. But you know, I urge you to, like, before you go and say, I'm gonna go invest in fine tuning, make sure you've done your due diligence to go through prompt engineering, because that often will give you more flexibility if you can do this on standard models without going into fine tuning and all of that effort. So, okay, I did all the prompt engineering, but I want to host my own model because whatever reason. And for many people, that may just be, I don't trust OpenAI with my data, right? I needed this be internal. I want to use a model that's different than that. There's 1,000 different reasons, but once you've gone past that point where you've ruled out these token-based systems, then you're thinking about like, okay, well, I need to host this, or I need to find a vendor who can host this for me. And I kind of get into the situation now thinking about, well, what does that look like? So particularly for workloads that are based on user input, we tend to see this kind of thing. We have different times where we have less workload, and we have different times where we have more workload. And the easiest thing to do is to go buy enough GPUs in order to satisfy our peak demand. But if we do that, you know, we're going to spend most of our time in this area of where we're way underutilized and we're paying for resources we don't need, right? And I see there's tons of this going on right now. And I think, honestly, the CSPs have created some of their own problems in that if you're a startup, AWS, Microsoft will give you basically like $100,000 of credits. And right now I've talked to a bunch of AI startup companies that are like, AWS gave us $100,000, and so we went and rented that $32 an hour system, and we're running that, but we don't care because it's not our money. And now there's a GPU shortage because we're way underutilizing what's out there. So we think about like the number of resources we have, well, I can start thinking about how do I scale my workload up and down to actually use that appropriately. And you know, each of the solutions out there, like EC2, I can do auto-scaling, Kubernetes, I can do horizontal auto-scaling. There's lots of different ways to sort of solve this challenge in order to use the resources more effectively and try to bring some of that down. And there's a paper written by a person at AWS who was instrumental in building Lambda. I talked through a bunch of different pieces here, but one of the things he talked about was Little's Law, right? And that's the amount of work that can get through a system, right? So the throughput of the system plus the time it takes to go do that and equals like your work in progress. It equals your queue. And at some point you think about it as like a teller at like a store. If there's one teller and they can process one person every 2 minutes, and if more than 2 people or more than one person is coming to the store every 2 minutes, eventually you're going to start building a queue. At some point, you're going to reject people from that queue because the queue is going to become so long that people are like, no, I'm not going into that store. There's 80 people deep. It's not worth my time. And we have capacity constraints as well. It's like a lot of stores, like 80 people might not even fit. Particularly if we've got 80 people in there and there's one teller, there's problems. And we have ways that we can go like increase throughput, right? We think of scaling. I can do things that are quick, like I've already got another person employee in the store, bring them in and have them work a second register. I have things that are longer, like I can go hire more people, I can open another store, I can get a bigger store, right? There's a lot of these controls we have, and we have very similar controls in IT and like how we're going to scale our cloud services. One of the differences, though, is we generally don't want to leave things in queue. And so we see this graph in the bottom, right, where we have the number of clients in the system versus our utilization. And that's really where we start hitting here above 80, 90% utilization. The time it takes to process this starts to skyrocket because we're used to having no queue and being able to solve everything right away. And then we get a queue and suddenly things go up very quickly. But we can't process more than what the system's capable of. So this is where we ultimately try to provide scaling to prevent ourselves from really crossing that critical point where the function starts skyrocketing the latency. And so like, when do I need a scale, right? Well, the time to add your capacity times divided by like the maximum change that we think this is going to happen. And for this, we're looking at like gigabyte seconds of GPU that I'm using. That's the amount of spare capacity I need, the point where I need to scale. So if I decide like, hey, my system can take 1,000 and the maximum, it takes me 10 seconds to go change it, and the maximum change here is going to be 210 seconds, then I basically need 800 gigabytes, in order to solve that. Of course, we also have to add in the fact that autoscaling, we tend to put delays in there because of how autoscaling tends to be expensive. It goes up and down. If we just momentarily peaked above our limit, we don't want to spend seconds or minutes spinning up more infrastructure. So usually we're going to delay after we hit that limit, make sure that we're really over the limit, and then we're going to scale. And so ultimately we see something like this. This one references containers, but we do the same thing in virtual machines, et cetera, where we're always over-provisioned because the moment that we hit our threshold, we're going to have to start scaling, spinning up the next box, because we never want to hit a situation where my workload has exceeded my capacity, because then we see what we saw in that graph before, our mean time to deal with those clients skyrockets, and then ultimately we start rejecting. So we think about this like in terms of LLM inferencing, right? Like you can handle this and build this yourself, and you have to think about this if you're scaling up and down and don't want to be over-provisioned the whole time. But even if you're using a token-based solution or somebody else is hosting this for you, you're still going to have these, they're going to have these challenges, and they're going to pass those challenges on to you, right? So if I think about a vendor that say may provide me serverless functions or serverless AI inferencing in a container. Solutions that are out there today take something about 90 seconds to start up. So I have to think about that in terms of delay. And because of that huge performance penalty in the front end, usually you keep the thing on for like at least 15 minutes because I don't necessarily want to pay that penalty again. Well, how does this actually impact the costs that I spend, right? And I think it's important that people think about your costs, like what they are charging you for your infrastructure, is inclusive of the costs that they have. And if they are wildly over-provisioned the whole time, then they're going to have more overhead, and they're going to have to charge you more. And most of these companies right out there are not actually using their own data centers. They're renting that from AWS or Microsoft or somebody else. So they're, again, passing that infrastructure along to you. Unfortunately, doing it yourself doesn't necessarily save you much, because usually the overhead of owning your own infrastructure and handling all these pieces tends to be higher for you. And a big piece of that is because of multi-tenancy. There's a concept of peak to, or average to peak, or mean to peak. And that if I have one workload, it's going to tend to have its own, there'll be the high point of the day, the low point of the day, and we'll often see some consistent trends around that. Right, so we see this with, NVIDIA has this problem with, they have a bunch of GPUs that they use for gaming, and about 5 p.m. East Coast time, these things start going up in usage. At about 3 a.m. West Coast time, they're down. But from 3 a.m. West Coast until 5 p.m. the next day, they're doing basically nothing, because everyone went to sleep and then went to work. But it's in the evenings where they're peaking, right? Versus we'd expect a lot of workloads that are driven by a company, we're going to see the opposite, right? We're going to see a lot of utilization during the day. And because these peaks and valleys, right, are relatively consistent, it makes it very difficult for us to do appropriate capacity, and it means we have to usually scale faster. But if I have multiple workloads, and in this instance we see a multi-tenancy of 2 versus a multi-tenancy of 4, our mean becomes much closer to our peak, because ultimately these different workloads overlap in different ways. The speed at which it needs to scale spreads out, and then we're able to offer this as a vendor more affordable than you would be able to even do yourself. And so that's, I think with this, it's still useful to go have the vendor do it because of this, and we won't have this internally unless you're a large company with lots of internal customers. So when we really look at the, like, how do we reduce our costs here, right? We want to look at paying attention to how our vendors are spending money and how our vendors' cost structure is. And so if the vendors are using technologies like containers, which really limit them on the number of containers they can have attached to a GPU, how much they can divide up that GPU, how fast things can deploy, and how long they have to keep it on, right? Like, even if they're only charging me for when they use it, they have all of those costs, and they're gonna need to bake those costs in to what they charge me. So if you can find vendors that can look at that in a new and innovative way and reduce their cost, then you can come up with more innovative solutions. So what is the net of all of this, right? What's the cheapest inference? And this is probably not the answer you thought I was gonna say, but it's the one you don't do. And this is one of the really, again, critical things. As I talked about prompt engineering before, like, don't jump immediately to training your own model until you've really exhausted what prompt engineering is. The same way is, don't think that, like, yes, this model is now consistently solving my problem every single time. We've hit victory. Because, like, if most companies, your workload probably is doing almost the identical thing over and over and over. Why would you have the most expensive resource do that? There's a really cool paper I liked called Frugal GPT paper. And basically they did several tactics. One of them was vector similarity search. We already use this a lot for embeddings, right? So like the augmented questioning, where I'm gonna say, let me do a vector similarity search, find the right piece of data out of all of my data and send that along, and then AI tends to turn a better answer. But you can also cache the responses and the questions that come back from when you asked AI, or when you did the inferencing, and you can store those and do the same thing. So I would say, hey, somebody asked another question. Let me, before I send this out to OpenAI or my internal system or wherever that is, let me look internally, like, have I been asked this basically the exact same question before? Yeah, let's return the cache response. There's no need to generate a new one. Likewise, there's a concept of cascading, where there's many much cheaper models that are much smaller than something like ChatGPT 3.5 that oftentimes will return a perfectly fine answer. And so by using, like, the confidence metric that comes back out of this, I can say, like, let's go hit the cheap model first, see if we get a high confidence level, and if we do, let's return that answer. And only if we have low confidence levels, then let's move up to the more expensive models. These kind of things can avoid a lot of the inferencing. So you look at how I could build my system, and I'm like, okay, the cheapest I could possibly get to is what OpenAI is gonna charge me at, like, 0.35 cents or something per token. Well, that's not really true. Like, the cheapest that you can get is to make sure that not all of your requests actually go to the really expensive big model, and a lot of the requests never get there. So how do I put this all together? Well, ideally, I want a solution where I have I either am myself or using a vendor, which is gonna drive down those overhead costs that we talked about, and is gonna give me the ability to have tooling that's gonna make it really easy for me to support multiple models and to do vector similarity searching by having a VSS embedded or enabled database. And you see right now, like, it's really dependent on you as the end user to go wire all this stuff up yourself, right? And I was at an AI conference a couple months ago in the city, and like there was, I think, 6 vendors there that had vector enabled databases. I'm like, cool, like, that's a problem we have today, but like, it's weird to me that, like, hey, I as OpenAI or any scale, any of the people that are gonna host something for you is gonna say, you totally should do vector search. You should be using that. I'm not gonna help you in that in any way, right? And you need to find a new vendor and wire all this stuff up yourself. So finding a solution where you can absolutely do that, but find a solution where you got this all stored together can make this much easier. So that brings me back to Fermion, the company I'm with, we released a AI service back in September, right? We are a serverless functions company. We're in the business of time slicing CPUs, and we found a way to make it really, really, really efficient and fast to time slice CPUs to provide serverless capability. And we realized that we can time slice GPUs in a very similar way and provide a more effective, better utilization of the very expensive resources, and then do that in ways where we don't waste tons of time starting up and loading like an 11 gig model into a container and into the GPU memory. Like, let's cache that in the memory. Let's find a way to securely sandbox this with WebAssembly, and then throw this stuff in a queue and very quickly, within milliseconds, start handling your inferencing. And so we think of ourselves as like the next wave of cloud compute, right? We're not a replacement for containers, same way as containers weren't a replacement for virtual machines. But a lot of what we're doing is trying to minimize what you as a developer need to think about. You shouldn't have to sit there and think about, hey, I'm going to go build, I need to think about the infrastructure, I need to think about where this is all going to land, I need to think about scale. You know, we really allow you to just focus on write your application, accept a request in, get a response out. You need a KV, we've got that for you. You need a database, we have that for you. Vector search enabled. You need AI inferencing, we've got that for you. You just say LLM inference, and it's there. And so this is really where we get at the end, right? It's like we think about how I can optimally use these resources. We make similar single requests, and then I can much better target the workload that I have because I don't have to over-provision. So there's a few things for call to action here, and then I'm going to show something really quickly demo-wise. But we've got our quick start if you guys want to get learning with it. Again, another link to our AI, the white paper that we've got. And then IDC released a report on us recently that goes through both our serverless functions and our AI inferencing. So before we are done, I want to show this is llm-explorer.fermion.app. You can all browse to this if you want. And this is basically just a simple UI on top of, so this is a serverless function that is built on top of our AI inferencing. And so you can create a bunch of different applications. And this is a lot for making it easier to do that prompt engineering and understand how do I do this better. So here, we basically said, hey, this is the system prompt. I want to do sentiment analysis. I've given it a few shot examples of what's going on. And then we control the tokens, the temperature, repeat penalty, et cetera. Make that really easy. And I can go here and say like, was this talk great? Oh, is it not showing that? How do I move system settings, displays, arrange, no, there's mirror. Mirror extend to Daddy Mac? I don't think that's what I want. All right, you know what? I'll just drag it over here. You see it now? Now, I can't see it, but see the writing. So I can't see anything on this thing, but now you go there, you're welcome to play around with it. We've got ones for sentiment analysis, asking questions, you know, generally helping you know, people if you want to have a, like, let me have a helpful chatbot, et cetera. Identity recognition, like identifying within a paragraph what are the actors in that. So there's a bunch of examples. This is just one for sentiment analysis, but again, lets you play around with this really, really easy and top of Code Llama and Llama 2 and see what's going on. So that's my chat. Happy to answer any questions anyone has.